Okay, welcome everybody. We're going to go ahead and get started. So pretty exciting night, our first meeting as a return actually to the Detroit Observatory. Some of you know we were here many decades ago, and I've been in the club for what seems like forever. And it was even shortly before I had joined the club. But we do have some like Doug Nell, for example, Jack, that do remember when we were meeting here quite some time ago. So it's kind of cool. Now we're returning into a new part of the building, but still seems rather nice. It seems appropriate that we're meeting in an observatory. So it's rather nice. And right now I would like
question.
Yes.
Back then we were given our own key.
So we'll take that as a hint that probably will be a denied, but anyway, next try though. Yeah. Anyway, I'm Charlie Nielsen. I'm president of this club. Most of you know that, probably some of you don't. So I've been the president for it seems like forever. We have a few other officers here, and we'll get some reports from them, but not until after we have our guest speaker, because many of you are probably here for that and don't necessarily want to be bored with our business meeting. So but before we get to that, I would like to bring up the person that's responsible for being able to bring us back here, Austin Admister. Yes.
Hello, everybody. Welcome, University of Lowbrow astronomers, back to the Detroit Observatory. Our historic facility from 1854 to today has been a very important piece of the university's history through astronomy, through meteorology, through architecture, depending on who you talk to. And for a while, the Lowbrows met in our original facility. If you could make it tonight through the tours, the Chronicle room or the libraries, we have it, was the sort of conference room for these meetings in the past. And unfortunately, that did not continue. And we're really excited to bring you all back here now to this brand new facility that connects us directly to the original facility. If you came in the past, you might remember a very terrible, tall stairway coming off of Ann Street to the front door. We now have this beautiful observatory street access where we can come in on street level, up an elevator or new stairway, and pass this wonderful classroom. So this classroom, a state-of-the-art classroom with all of the top level technologies and audiovisual systems that the university can offer, has allowed us to open up programming, talks, presentations, and now be able to bring the Lowbrows back to the observatory. So we're really excited to have you back here. I'm excited to actually be able to kind of sit in on meetings more often now, because for most of your meetings, I've usually been here at the observatory for our astronomy nights. And after the meeting tonight, I encourage you to visit the observatory. We are sort of right back in action, doing tours through the building. We, of course, can't observe tonight, Michigan weather, but we will be observing with the telescope whenever possible under clear skies. So as you come back to meetings, I hope that a chance arises again soon. Otherwise, thank you so much, Charlie, for
thank you. Appreciate it. Okay, so with that, I'd like to introduce our guest speaker for tonight. And he is coming to us via Zoom because he is residing in the great state of Maine. So it's a little bit of a drive for him. But our speaker is Dr. Jeff Morganthaler, and he likes to think of himself as an experimental physicist whose laboratory opens to the sky. He has used a comet to measure the ionization lifetime of carbon, is using Io's atmosphere as a probe of conditions in Jupiter's magnetosphere, and has constructed a small aperture coronagraph to monitor and measure Jupiter's magnetospheric response to large volcanic eruptions on Io. This coronagraph also records spectacular images of Mercury's sodium tail and comet Neowise sodium. Dr. Morganthaler received his PhD in 1998 from the University of Wisconsin, where he studied the spectrum of the diffuse X-ray background with a space shuttle payload of Opportunity and a sounding rocket employing one of the first single photon calorimetric X-ray detectors. Say that fast. He was subsequently a National Research Council Fellow at the NASA Goddard Space Flight Center, where he studied the Io plasma torus and created the parameterized function object system, a robust function fitting package that can be used with AI techniques to emulate the decisions of an intelligent data analyst. Then he was a research scientist at the University of Washington for about 4 years, studying comets. In 2008, he joined the Planetary Science Institute. In 2011, he became responsible for leading PSI's internal proposal review called the Red Team program. And in 2017, he became the PSI Observatory manager. Jeff has won numerous awards dating back to 1989. As you will discover during this presentation, he has a connection to Robert McMath, who, as many of you know, is the builder of our precious telescope at Peach Mountain. And we're going to hear about that during this presentation. But with that, you didn't come to listen to me. So I'm going to please welcome Dr. Jeff Morganthaler.
Well, thanks very much. And my connection to the club comes through Ken Cook, whose daughter married my godson. And that's how that connection was made. And I also see that Jeff Kopmanis, I don't know if that's how you say it.
Yeah, right.
Yeah, plays Barry Sachs, which makes him a cool dude in my book. My favorite instrument in school when I played. Here to talk to you about studying volcanic activity on Jupiter's moon Io using equipment you can buy at a high-end camera shop. And I'll need to qualify a little bit more later as well. Thank you for inviting me. Okay, the first thing I need to do is alert you to jargon that will just roll off my tongue without my even thinking of it because I use it so often. Jovian means of or pertaining to Jupiter. So I'll be talking about the Jovian Sodium Nebula. That's a nebula of sodium around Jupiter. And in case I forget to mention it later, sodium is really easy to observe as a gas around anything really, because it has a very bright or a very efficient atomic transition. That's why they used it for those yellow sodium vapor streetlights. Okay, just tickle it with a little electricity and it lights up very efficiently. Similarly with sunlight, with a little bit of sunlight, you get a lot of sodium emission back, almost like a mirror. That'll come up later. Okay, and RJ, our sub J, Jovian radii. That's kind of like the astronomical unit of the Jovian system, right? It's the yardstick we use to measure how far out things are from the center of Jupiter. Okay. Oh, one more. Okay. Need I say more? So now you can understand the words in my outline. I'm going to start by talking about Robert McMath, and then Jupiter's moon Io, and how the material from Io makes the Io plasma torus. I'll show you what that is. And the Jovian Sodium Nebula. I will show you what that is and how these three work together. It's kind of a chicken and egg thing. So I'll have to talk about one and then the other, and they feed back and all that. So you might need to suspend some disbelief on some of my descriptions. Okay, so I then talk about the Io Input-Output Observatory, or IOIO. And that's the telescope you see behind me. Now, full disclosure, there are some special parts required, but you can actually buy them at a particular high-end camera shop, or make them yourself on your home lathe. Anyway, and then I'll talk about first results, which I'm writing a paper about right now. And then projects related to IO science or other projects that are accessible with no special equipment, just a telescope. CCD cameras are helpful, but even without CCD cameras, you can do useful things. And then entertain questions. Okay, so I forgot to reset my timer here. The role of Robert McMath in my career, well, he died 10 years before I was born, so I wasn't directly meeting him, but he was one of the motivators behind the founding of the Cape Peak National Observatory. Probably maybe familiar with the story that he was on an NSF advisory panel that basically said, hey, this would be a good thing to do. Make one place for astronomers, American astronomers, and then, eventually became a gathering place for astronomers around the world with, top of the notch equipment for the 60s, and was active for decades before it kind of got supplanted by other places like Hawaii and Chile. And there's still telescopes up there that are doing productive work. Anyway, one of the anchor stores in the mall, if you will, was the McMath Pierce Solar Telescope. That's this funny looking upside down check mark, okay, buried in the ground. And the other side, the other anchor mall was the 4-meter telescope, although maybe this 2-meter telescope did come first. Anyway, so I actually went there first when I was a senior at MIT in 1989. I apparently met somebody famous at the lunch table, but I don't remember who. That's what my advisor said. Oh, this person's famous. But I have met some famous people there over the years, and it's been pretty cool. Robert Kennicott, who was, anyway, I won't go into my list. Anyway, so the solar telescope, though, I didn't start using until 1997. And for 9 years, however long that is, I can't calculate, I used it at night. And the reason we used it at night is that it doesn't get too busy. Solar telescopes are undersubscribed at night, and we were studying something highly dynamic, and we just needed a lot of time to look at it. And of course, telescopes work night or day, particularly the McMath Pierce Solar Telescope. Keith Pierce was a well-known scientist of the day, and so they named that after both of them. I actually have met Dr. Pierce, asked him what it felt like to have a telescope named after him, and he said, "Oh, just means I'm old." So anyway, the cool thing about the McMath is you can look anywhere on the sky any time of the day, and it's safe. Okay, it has to do with super long focus, focal length, and super long F ratio. Anyway, so how it works is you get this light coming in from the sky. It's steered by the number 1 mirror, which moves around, down to the number 2 mirror, which is the focusing element. Okay, and that goes to the number 3 element, and that just reflects the light to go straight down into this observing room. Okay, there I am pontificating to my colleagues 20 years ago. And this particular table is just the top of this 60-foot long tank. And that tank contains a high-resolution spectrograph that was used for solar astronomy. There's another tank off to the left, and you can move the mirrors around. It's cool, huge tracks. It's a fun place. Anyway, then in the background, actually background and foreground, there are 2 other telescopes. They're smaller, 0.9 meters instead of 2 meters. And if you look on that back wall to the right, and if we had set it up, we only set it up during a couple months a year we would be there. Here is our plasma torus imager. It was built by an undergraduate with a little help from an instrument builder. Used an old style liquid nitrogen cooled CCD, and had a special focal plane instrument, and I'll show you the details of the one that's on IOIO. So I won't describe this too much other than to say it was there, and that kind of got me interested in the plasma torus because it's a really cool thing. One more mention about that big tank to the left. It is a spectrograph that it's the only spectrograph that's been able to monitor Io's atmosphere while Io has been shining in sunlight. Super high resolution and big field of view, which is a very unusual combination. Anyway, that's a talk for another time. Okay, so here's the Io plasma torus. This is the highest spatial resolution set of images, okay, taken by a colleague of mine who actually also gave me a sailboat. So I like him for many reasons. His images here show you one of the key things you need to do when you're taking images of the plasma torus. First of all, plasma torus is ions trapped in Jupiter's magnetic field. It rotates around really fast. And I'll explain all that in the next few slides. But I wanted to point out here that Jupiter is behind some sunglasses material. Excuse me. It's a coronagraph, okay, but unlike a solar coronagraph that completely occults the sun, this one attenuates the central object by a factor of 1,000, give or take. And so that lets you still see that central object, get rid of most of the nasty light, and then image faint gas around it. Okay. So, unfortunately, even as I started using the solar telescope in the late 90s and early 2000s, they were definitely making noise that they were decommissioning it for science activities, which has now happened, but it has or isn't the process of being recommissioned for outreach in a really cool way. So, and plus it's still there for like, well, I don't know how much of it is closed or open at the particular moment, but other places on Kitt Peak are open definitely for outreach purposes, some of the telescopes in the visitor center. So if you ever get a chance to go out to the Tucson area, drive west for about an hour, and you can go up to Kitt Peak and see what's there. Okay, so that beautiful image, and the 0.9 meter telescope took, images that weren't quite as fancy. So, but you can definitely see the torus wiggling around and all this cool stuff I'll show you more about later. And I was just hooked. So I wanted to continue doing science. And I knew I couldn't do the spectrograph thing, as that there's only one on the Earth that did that. So imaging, that was what I was going to be able to do. Okay. And so I'll show you how I've been able to take torus images and bonus sodium images. Okay. So this is what IOIO has been able to do, but it wasn't like I could wave the wand and have it up into existence immediately. Okay, well, let's go into a little bit more of the outline there to understand what you're really looking at when you see that beautiful ring wobbling around. Okay, so first let's talk about Io. It has the highest density of surface volcanism of any object in the solar system. I think that is absolutely right. It's not the most volcanic body because, the Earth has probably more volcanoes, but anyway, the reason Io is so volcanic can be seen down here. You see Io going around, like say twice for every one time Europa goes around, or 4 times for every one time Ganymede goes around. That's a tidally locked system. And because of that, I was always either pulled out or let to relax in towards Jupiter. And it's that modulation distance from Jupiter, in particular, motion in Jupiter's gravitational field, you get gravitational field gradient changes, that ends up squeezing and relaxing Io like a cosmic anger ball. Okay, so that couples heat in, and it really does that for all these satellites. for Io, it's hot enough to melt rock. Okay, here you see some of that melted rock leaking out in the form of lava, as shown in this infrared image. It's volcanoes, so you get plumes, big ones, medium-sized ones. They're probably little ones too. And then Io's surface looks like a moldy pizza, because you have all these sulfurous molecules. Okay, it's SO2, sulfur dioxide, but then ones that are longer chain, sulfur 6, sulfur 8, all kinds of weird things. Now each one corresponds to a different color here. This, for instance, this black stuff is lava. I think such low key. Anyway, they all have names. So Io gets hot enough to melt rock. Europa hot enough to melt water. Okay, and Ganymede as well. So one of the cool things about Io, though, is this volcanism allows it to maintain an atmosphere. Not very much of one, but it's still there. Okay, so let's look at what happens when that atmosphere gets bombarded by the particles in the plasma torus, which are going around very quickly. You get this sort of chicken and egg dance. So I'll explain more about the plasma torus and why it's going around quickly in the next slide. But imagine that you have these high velocity, 80 kilometers per second, smacking into Io from the left. Okay, and these three processes are the primary things that go on. You've got billiard balls. Okay, atmospheric sputtering. You have just an ion hits a neutral atom in Io's atmosphere and knocks it off to the right. Actually, it knocks a bunch of them off because it's very, it's like doing a break in a billiard table. Boom, they all go flying. Okay, and many of them go knocking back. And I'll show you more details about that later. Ionization. Well, that's a pretty easy one. You have, say, an electron. It splits apart neutral, splits one electron off, and it becomes an ion, and that joins a plasma torus. That's kind of the chicken and egg part. Plasma torus begets plasma torus. All right, then this other one, a little abstract. You could think of it as just neutralization. Sometimes the electron goes in the other direction. It sucks back onto your plasma torus ion. It was zooming fast, and it all of a sudden is a neutral. And it doesn't feel the magnetic field anymore. Hope you understand that. I'll explain a little bit more about that. And then it just goes flying off because it's not confined to move in Jupiter's magnetic field. Now I'll show you that. It's really cool. We can see that in sodium. Okay. So now, okay, so taking a step back and bringing more artistic pictures in, we see Jupiter here in the middle, Jupiter's magnetic field in blue, the orbits of Io, Europa, Ganymede, Callisto. And so here's the plasma torus, this red thing. And then it's kind of depicting the billiard ball collisions, the sputtering that knock material back behind Io. Okay, that's in yellow. And then, of course, the chicken and egg thing of the plasma begetting plasma in the plasma torus. This is why this is red. And it's kind of red throughout because the plasma ends up diffusing out and smacking into the other satellites and filling the whole magnetosphere. Pretty much all the material in Jupiter's magnetosphere comes from Io. And again, magnetosphere is the domain that's dominated by Jupiter's magnetic field. Okay, the solar wind is out beyond that. Okay, one more thing here I won't talk about in detail, a whole nother cool talk, is the Io flux tube. If you've ever seen the movie Avatar, they've got those island things floating in the sky on the flux tube. It's motivated by this. Okay, what happens when plasma hits Io some of it gets very excited, and it still has to follow the Maxwell's equations. It goes along a magnetic field line at very high energy, these electrons, and then go crashing into Jupiter's magnetic field and cause aurora, okay, at the poles. It's not this ring aurora, that's from something a little bit farther out. It's a sort of a tadpole-shaped thing that's anchored and always follows the magnetic field line that's attached to Io. It's really cool. Okay. So why a torus? All right, well, I'm not going to bring out Maxwell's equations on you, but just to know that charges will spiral around a magnetic field. Okay, and I've tried to indicate this with this toy here. Okay, here is this red loop, okay, or coil, indicates the path of charges, electrons and ions. Okay, and the magnetic field in this case would go straight through that. Okay, and the stronger the magnetic field, the more squished in those charges would be. It can run the other way. If that really, well, it is a wire. If you pushed an electric current, okay, if you push those charges through with a battery or something like that, you would generate a magnetic field. Okay, that's, Mr. Maxwell's equations working for us. Okay, now picture that little coil miniaturized and placed inside of that arcing yellow wire. Okay, and so then these beads are just kind of blow-ups of all the little beads spiraling around on that miniaturized wire. Okay, now take that toy and spin around really fast, and your intuition tells you, oh, those wires will collect out here at the farthest point. Okay, well, that's exactly what's going on with the plasma torus. Okay, charges are sort of these things on wires, and they're confined to the magnetic field lines. And the balance of forces, given that Jupiter rotates every 10 hours, that's really fast. Okay, big planet, huge, strong magnetic field. Okay, 10 hours. And so these plasma, at least the thermal plasma, okay, not that stuff that's really high energy making the flux tube. Okay, but the thermal plasma is just going to hang around in the plane of the magnetic equator. Okay, so that's why is this tilted? Well, Jupiter's rotation axis does not, its magnetic field axis doesn't cooperate and line up with its rotation axis, and just like the Earth's. Okay, and it's about 10 degrees, 12 degrees, something like that. And anyway, so that's why this is tilted, and then you get this sort of cone angle, which is why you saw the plasma torus wobbling in that series of images. And then I'll show you an animation of that taken with IOIO soon. And then the final thing, you see some of these charges climbing up field lines. Okay, that's from thermal motion, that they bonk against each other and kind of chase each other away and climb up the field lines a little bit. We can use that to measure the temperature there. Okay. So the sodium nebula has its origin in those knockback particles. Okay. They're neutrals that end up, this yellow stuff, knocking back and making a banana-shaped cloud called the banana cloud behind Io. So what's going on is that the plasma torus is rotating counterclockwise here. And so when the plasma bonks against Io, it knocks stuff back in this direction. But that neutralization process is also operating, that your plasma that grabs its electron back, becomes neutral and no longer is confined to, follow a magnetic field line. It just goes straight off. And it's going at 80 kilometers per second. It's not stopping for nobody, okay? Because the escape velocity of Jupiter at this distance is much less than that. So it goes off for a long time. And then, so that's called the stream. You'll see why. And there's another feature called the jet, which is a little bit closer to Jupiter that when you first start to pick up a ion and it gyrates around a partial, wire, and then it happens to neutralize, it goes off at kind of a weird angle. And that weird angle is here, and it's also sort of up and down as well. You'll see that in the movie. Okay. So here is an image from that 1.5 meter telescope that I showed you at first, the image of the plasma torus. This is now in neutral sodium. And the ion we use is sulfur. So it's a nebular filter, basically. S plus 6731 is the line I use. This would be 5890 angstroms. So that's yellow, orange, those colors. Okay, so here you're seeing the banana, which, because those atoms end up orbiting Jupiter as much as being bonked, they just collect in the orbital plane of Io. And the stream, though, is like freshly ionized stuff or neutralized stuff that's just winging out at whatever angle the plasma torus was tilted at, okay, at least from our perspective. And so this thing is going to end up flapping up and down, which you will see. Now, if you look far away, this is about 15 RJ diameter. Io hangs out at 6 RJ. That's its orbital radius. Okay. But this sodium nebula ends up being 1,000 RJ wide. They're 7 degrees, maybe even more, from the perspective of the Earth. That's actually the largest thing in the solar system, except the heliosphere. I won't go into too much detail about what the heliosphere is, but it's, anyway, this thing's big. And I already talked about why sodium is bright, because it has an efficient electron transition that's stimulated by electricity or light. So yeah, there's hardly any sodium in the system. It probably comes from salt, but you just need a little, and it's very bright. Okay, so back to IOIO. So handwriting was on the map here, solar telescope, and I was scrambling around for how do I build my own telescope or find something that'll do these observations, because it's a highly dynamic environment. It's always changing, it's always wiggling and getting brighter and dimmer due to other things. It shifts to the left and right as material goes down, like away from the sun, from Jupiter. You just gotta stare at it all the time. So Tohoku University in Japan used a 12-inch portable telescope to study the torus. Okay, that's affordable. And Boston University and Tohoku University used these 3-inch telescopes to image the sodium nebula. Now, of course, larger telescopes work for all this, but good luck getting time every night on them. But they also have the disadvantage of smaller fields of view. And for the sodium nebula in particular, if I wanted to kind of have a comparable experience as those wide field coronagraphs, I wanted as wide a field as I could get. Okay, and that's 15, maybe not. Okay. Well, while I was cogitating this and talking with some people about preliminary optical designs and everything, I heard about Jeff Baumgartner's experiment in his backyard. Jeff Baumgartner is the, let's see, well, anyway, he's an instrument builder at Boston University. He's the one who designed their 3-inch chronograph and all kinds of cool stuff. And I was at a talk he gave, and he showed a movie of the sodium nebula taken with his C-14 in his Boston suburb backyard. Okay. So that, I believe, is what sold the project to the NSF in 2015. So that I've been funded ever since then on this project. Very thankful for that. Okay, so let's talk about IOIO. Well, it's a C-14, so that's around 14-inch optical tube assembly. And I don't know how much time we want to spend on being nerdy about telescope stuff. I'm happy to do that maybe afterward. One of the key things about this thing that makes it tenable for me to run this for the last 6 years and still be happily married, right, honey? Is that I can't stay up every night, you know, for 6 months at a time, because Jupiter kind of goes behind the sun for, you know, a few months and then it comes back out again. That first year, before I got it all roboticized, yes, 2 weeks at a time, I would stay up and it was a mess. But you know, there are any number of commercial products that are marketed to amateur astronomers that can be used to assist the roboticization. I had to do some scene recognition and stuff like this for the coronagraph, but that's okay. I'm a scientist, I do stuff like that. But all that other stuff, I didn't have to worry about. It was just plug and play, all this hardware and some software. Really great. Okay, so the only special thing I needed was a coronagraph. Okay, that's highlighted here in green. Basically, that just plugs into the back of the telescope as if it were a camera. Okay, camera normally, this is the camera back here, this thing with a fan. That normally would sit here on the back of the telescope, and just insert the coronagraph instead. Okay, so Jeff Baumgartner had the optical design and a specific design that was really easy to plug into sort of any C-14. Scott Tucker at Starzona came up with. Now, Scott has a series of YouTube videos about doing all kinds of things. You know, he's a great resource for amateur astronomers. And they're actually willing, you know, they have the plans for this and willing to help people build this, probably for a price. I don't know what the price would be. You know, it's just, I'll show you, it's just a tube with some mounting points for a lens and on one end and another lens on the other end. And then it plugs into a standard filter wheel. Okay, so here, let's unpack it a little bit. Fun. So here is the tube. This is the full assembly. If we take the filter wheel off and put it on the table, you see this ring here, okay, that's screwed on in 3 places. You just take that ring off and replace it with this funny insert thing, which puts this coronographic strip, our sunglasses material, if it's plastic rattan gelatin ND3, if you must know, and that inset puts it as close as possible to the front of the filters. Okay, and so here you're seeing the tube, you know, machine drawing, and that this is indicating the filter and coronagraph assembly. Here's the ray tracing. This is where the telescope focuses. And if you know anything about optics, once you come to a focus, you don't like to stay there. The rays diverge on the far side. Okay, so you need another lens to help you out. and make those converge back towards your CCD. Okay. And the way it's done here is have them converge so they fit into the bundle of rays fit inside that, the entrance to your lens, so you don't lose any light. And then you focus that lens. It could kind of be focused anywhere, but you focus it on the focal plane of the telescope. So they kind of match each other. And then when this tube stretches or shrinks due to temperature, right? That's why telescopes go out of focus. You just change the rack and pinion thing back here, which can be done mechanically, through software. It's all, amateur available stuff. And that moves the tube back and forth and you get focused. And again, there's nothing special, but the one thing you have to do is focus this lens, just do that once. And this is what you see. Okay, again, you're looking at what the CCD sees of this, neutral density strip. Okay, you see Scott had to cut it with a scissors or something like that, so it's a little bit raggedy on the edge. That's okay, I'll just take care of that in software. And here, what you're looking at over here is the filter wheel. I've got a standard broadband Johnson Cousins R here, and then two sets of filters. I'm not going to get into too much detail about how they work as for off-band and on-band, but basically, say this is the sodium on-band filter, meaning that the sodium 5890 angstrom emission goes through that, along with some parasitic scattered light from Jupiter. You can't get away from that. All right, no matter how narrow you make that filter in wavelength band, you're still going to get some continuum from the scattered light. Well, you just go to another pass band on one or the other side in wavelength and measure the scattered light over there with no sodium, okay, and then subtract. That's all that does. So I got a pair for sodium and a pair for sulfur. A little bit of fine print. Those filters cost $16,000. Okay, $4,000 a piece. So that's kind of where NSF helped. But there are some cheaper versions of the sodium in particular, well, and the sulfur. It's the nebular filter. I don't know if you'd be able to detect I'll show you what you can detect with cheaper sodium filters. And that has definitely been done by many amateurs. Okay. And then there are other projects I'll talk about that can be done with no coronagraph. And here's some of the data. So not quite as fancy as my friend who gave me the sailboat. It's not a 2.5 or 1.5 meter telescope. It's a 35 centimeter telescope. Okay, but you're looking at the plasma torus, looking a little bit more donut-y when it's not quite such high resolution. And it is wobbling because of Jupiter's magnetic field tilt relative to Jupiter's rotation. And I will show you how I do all this complexity. So in the middle, you see Jupiter. You see the plasma torus wobbling around. And then you see these nasty Galilean satellites wandering around. Not much you can do about those. Okay. Here is the sodium nebula. Plus a little bit of artifact every now and again from over subtraction or under subtraction of in the background there. But what you're seeing here is the jet and the stream. Okay, so if you follow, one of those dots is Io, and occasionally you'll get these amazing streams off to one side or the other. And sometimes it splits because the jet goes in one direction and the stream goes in the other. The reason it flips around and it's not continuous is because the sun does rise on the Io empire. Okay, sorry for the imperialistic reference, but the solar astronomers did a thing, Global Oscillations Network. They actually had stations, like 7 stations around the Earth that could look at the sun all the time and study the highly dynamic things on the sun. Okay, I guess they rate more funding. They could do that. But the same thing could be done with multiple IOIO stations around the globe, the Earth globe, and we wouldn't have these gaps due to daylight or weather. Just a dream. So anyway, that's the raw data. And now I'm going to move towards how I am processing that to get some first results published. Okay. Again, this is as we speak, and we're running it just this afternoon paper. So instead, I mean, because we have mathematical models to describe all that wiggling and the temperatures and the shifting and all that, and eventually that's all going to be, part of the analysis. But I'd like to do things in a incremental way. And the very first thing is just put boxes around these edges or anses, which is apparently some Latin word for handle, like jug handle. And I get a little bit more fancy extracting light there, but basically I'm just extracting light from those ends. I do a similar thing with the sodium nebula. Okay, so here I use these boxes that are increasing distances from Jupiter, and I add up all the light in the ones of similar color. Okay, and they're bigger as you go out, just so I get more signal or comparable signal. But obviously the surface brightness, okay, the average brightness in this box is going to be much less than in that box. And I chose to do it in this above and below thing, so I didn't get all confused to the left and right, where this beautiful structure modulates so much left to right. At least up down, it's kind of all averaged. All right, so preliminary easy analysis or extraction for analysis anyway. So on the top, we've got the sodium nebula. Oh, sorry. Okay, what I did is I took each image generates 3 brightnesses, each a different distance from Jupiter. Okay, and the closer distances, like 6 RJ above and below, are the brightest. Okay, and the farthest is 24 RJ above and below is the dimmest. And so each one of these points is actually from a bunch of averages of images, all averaged each night. Okay, so it's a sort of a condensation of a lot of data. What you're really looking at then is the time modulation of the brightness of the sodium nebula. In those 3 boxes, they all track together. You can just look at the blue one and say, it looks like it gets brighter here and dimmer there, and so on. I'll talk more about that. Oh, wow, that one is really bright. Okay, and again, these are in years. 2018 was when I really started full observations, and up till this past fall. Okay, the Io plasma torus, I had boxes to the left and right, and those are plotted in blue and red. The red, which is the one on the right, is consistently brighter for reasons of the plasma torus being shifted. I won't get into how that works, but it does. So these lines are the moving average through all those points, and these dark points are the moving average through all those plasma torus brightness measurements. Okay. So here's some science. Very simply, nobody else has been able to do such a long-term study. Okay, that was one of my motivating factors. just stare at it for a long time. And then this very simple experiment becomes what they call low-hanging fruit. Okay, you just, look at it real quick and say, huh, look at that. No one noticed that before. Okay, so, just real top levels, we see enhancements here, 1 or 2 per year, and they're paired between, pretty much for every sodium nebula enhancement, there is a sulfur torus enhancement, a little bit shifted in time, and we understand that. But interesting, enhancement is the normal state. Okay, something's always going on. These quiescent levels here, which it does reach occasionally, is not the norm. So the average is determined by these, these spikes. And it's not always the same. I mean, these years it was pretty much the same. These sodium nebula enhancements were about equal, and similarly with these torus enhancements. Well, what happened to the torus here? I guess it got tired. Or all the energy went into the sodium. Who knows? That's a question that's worth asking scientifically. Okay. So my current thinking, like as of today, the enhancements are probably plumes. But it's not quite a simple conclusion to come to scientifically. That's kind of where I'm at. That suggests that because that's normally what's going on, right? That these plumes are what's pumping material out into Jupiter's magnetosphere. See, kind of the prevailing wisdom has, Io's atmosphere sits there, material stripped off, and it's its quiescent atmosphere that's pumping material out. No, it seems to be specifically plumes. That's my interpretation. And there are other things going on between why that all happens. Okay. So that's if you have a coronagraph. If you don't have a coronagraph, what can you do? A lot. All right. So you guys are familiar with the difference between photometry and imaging? I'm guessing photometry is where you, what was it? On the plasma torus, I kind of did photometry here. I just added up the light in box. Okay. Stellar photometry, a little bit more sophisticated, or well, whatever. You do it differently with Gaussian circles and all this stuff. And there's software already to do that. Okay. I should have probably listed this first. The AAVSO. Anybody in the room does AAVSO work? American Association of Variable Star Astronomers. I don't know if I see any hands, maybe 2. They have a lot of great material on how to do photometry of stars, how to precisely add up the light compared to other stars and see if the star is varying. Okay, well, that's something that would be very interesting to do with Io itself. It's one of the first ways Io was thought, or well, someone suggested Io had an atmosphere long before Voyager saw plumes. Okay, Biner and Cruikshank back in 1964, they saw Io got brighter after it came out of eclipse from behind Jupiter. Okay, it does that every 42 hours. And why would it be brighter? And then within 10, 15 minutes, get dimmer again, back to its normal value. And I figured, hey, maybe some atmosphere collapsed onto the surface because the surface gets colder when it's in eclipse. There's no sunlight warming it up. And then when it comes back out, it warms up and sublimes the material that froze onto the atmosphere. And that generated a lot of controversy because somebody's single channel photometer didn't see it, but somebody's dual channel did, or vice versa. Like amateur astronomers have million channel photometers. Beat that. Okay. The professionals have kind of lost interest in this, in looking at the problem from this perspective. Okay, they use bigger telescopes and fanciful. I'd still like to see some measurements done on this. I've tried some with IOIO. I just haven't produced the data yet. Okay, it's not hard, and you don't need a coronagraph. You just need a CCD. Good anti-blooming helps. Okay, so other photometry transiting exosolar planets. This is actually data that was taken with IOIO. That's one of my other funded projects. When a planet, exosolar planet, goes in front of its host star, the star dims a little bit. And I'm working with a team of people who are studying ultra hot Jupiters. They're very close, orbit every 2 days or so, and looking for them spiraling in to their host stars. And then photometry works on comets as well, a little bit more subtle because you have a fuzzy blob, but you can do that to look for outbursts. That's a project I applied for funding on. And there's this really nice website that gives you all the comets that are bright enough for modest aperture telescopes to look at. Okay, so imaging, comet tails, okay, and Mercury sodium tail. So this is something, and here is a image taken by an amateur astronomer with a modestly priced sodium filter. Okay, I think he did some really nice image processing with, you know, multiple stacking in different colors and stuff. It's really good at that. But this is something you can see near dawn or dusk whenever Mercury's at elongation, and it doesn't cost a mint. So, and yeah, so there's Grant Jones is a scientist who studies ion tails, comet ion tails, and amateur astronomers have big fields of view and are able to you know, image those ion tails and do a great job. Here I'm sort of bragging because IOIO can do it in sodium, which is a little bit unusual. All right, time for questions.
Does Jupiter's third magnetic pole affect the torus in any visible way?
Does Jupiter's which magnetic field?
Yeah, I understand that Jupiter has a third magnetic pole, and I was wondering if that affects the results of the torus in any way.
Right. So Jupiter's magnetic field is distorted. It's not a perfect dipole. And so there is a little bit of a warp in the ioplasm torus. But where you see the really distorted magnetic field for Jupiter is much closer. And that's why the Juno mission is orbiting like within hundreds of kilometers of the cloud top. So they really get a good signal on that distortion.
Thank you.
Sure. Other questions?
More questions for Jeff? We always have more questions.
Yeah, I got one. Hey, Morgan, this is Ed. If you can repeat back, but you mentioned when you first got started, there was a lot of manual observation before you got the automation going. When did you think you had the automation down where you could sleep at night? How long did it
Well, in 2017, March is when I started. That was all manual, okay? And then maybe later that day or that year, or certainly 2018, I figured out my telescope enough to be able to start it up and then let it go automatically with some, you know, just the camera software, basically, the camera and the guider. That's all I was using. And then I could wake myself up a couple hours later when it was about to, there's a German equatorial mount, so it needs to like flip around or else it'll crash into the pier. I'd wake myself up at the right time, press a button, it would flip around and make sure it's all connected, and then go back to sleep. I did that for a couple months probably, and then yeah, the software, oh my gosh, it took a lot of work to write the software to do the scene recognition and everything like that. That wasn't until halfway through 2018 that I got that started.
Jeff?
Yeah.
Can you hear me? You mentioned at the beginning that you had done some work with the McMath Pierce, which has been shut down, as you mentioned, but you said that it's going to be open for outreach purposes. Do you have any hopes that you might be able to do some more work with it?
Absolutely. It just so happens, here, let me show you where I host IOIO. You can see I have a little roof collision potential here. Okay, so anyway, that's what those reflectors on the tube are for. But anyway, the guy who owns this hosting facility, he's got a dozen or so shacks like this or other things. He is the person or one of the people who's working at making McMath Pierce a outreach thing. Okay, they're going to put a science on a sphere in there. And the old machine shop. I love that machine shop. They are going to be using the telescopes to project images of the sun on the wall. And at night you can do the moon, you know, anything, but those are really dramatic objects. They're huge. It's like a yard across. And so yeah, they are doing the work to do that. And they'll be up before you know it.
You're probably aware that the Kitt Peak is still closed. It's been closed for a year and a half now because of some forest fires out there.
Right.
But and they've converted the McMath Pierce into a visitor center in addition to the outreach things you're talking about.
Right. That's in the I haven't been up there well since the fire, obviously, and yeah, it was a mess. The road was kind of destroyed, and so it's just taken a long time to get all that infrastructure up so people can safely go up and down without falling off. You know, there's no guardrails left though. Yeah, it's a mess.
More questions for Jeff?
Yeah, one more.
Yes, go
Hey,
ahead.
Jeff, it's actually again, what do you have to do to maintain it, to keep it dust free, that kind of thing, that kind of on face-to-face maintenance?
Yeah, it was a little bit hard during let's see, during COVID, because something did break and I couldn't get it replaced, so I lost some data. But one of the things that keeps it dust down a bit is this dew shield. Okay, it just makes it harder for dust to settle on, you know, the front of the telescope. And this particular telescope is a Schmidt-Cassegrain. Okay, so it has a glass plate on the front, just kind of a big lens, and there's a hole in that holds the secondary. Okay, so light comes in past that secondary, hits the primary here, and then hits the secondary, which is sort of embedded in this glass, and then back to, you know, the focal plane. And that glass has a little bit of a shape to it to correct for the fact that this is a less expensive spherically ground mirror. Okay, but the fringe benefit is it keeps dust out of this tube. Okay, so occasionally the guy who's out there doing the maintenance can just, you know, clean off that front. But yeah, it needs a little loving. I need to get out there and clean the filters and stuff. There's some dust donuts and things. I used to go out three times a year actually, but that's when I was, you know, I changed the filters and did things like that. It's been a couple of years since I've once. I was back in August, I guess, this past year. Other questions?
Where is the telescope?
Okay, the telescope is in Benson, Arizona. Okay, so here's Tucson, which is in southern Arizona. And then Benson is over here. It's kind of a widening in Interstate 10. And yeah, I didn't zoom out on this, but yeah, southern Arizona, it's about an hour east of Tucson, and Kitt Peak is about an hour west of Tucson. That's really good weather there. And no, it does not have to be on top of a mountain or anything. I'm looking at the fourth brightest object in the sky, or the third, whatever. It's not the sun, it's not the moon, it's not Mercury. Sorry, it's not Venus. It's Jupiter. So it dominates whatever's going on there. Yeah, Jim.
Jeff, are you aware that Robert McMath is a local guy here?
Yes.
From Michigan.
I do. I actually remembered, well, I didn't remember it when I signed up for the talk, but then it jogged my memory. And you know, the McMath Pierce, that observatory, so I was a graduate student in Wisconsin, okay, and in the 60s, when the observatory was built, immediately the instrument building people at Wisconsin in the physics department saw the opportunity, okay, because you could do all this work at night without much competition. And there was a huge room where you could build and deploy your instrumentation. You know, it's kind of a pain when you have a telescope, a normal telescope, where stuff is moving around in the back of the telescope. It's very not a friendly environment for delicate spectrometers, a specialty in Wisconsin. So this is the ideal place for that. And it was used for 50 years for that kind of stuff.
Any other questions?
Yeah.
Okay. Not saying any more. So how about a nice thank you for Jeff?
Thank you for being an attentive audience.
Not quite done though, Jeff. Just as a little small token of our appreciation, we'd like to give you a club t-shirt or a hat if you prefer. The t-shirts basically would look like this. And we have two styles of hats. One of them is this, which is kind of a low profile, you know, sticks down on your head. And then we've got another version, which is a more traditional type hat that's, you know, what you're more familiar with, higher profile. And I believe this one comes in two sizes. There's a large, extra large, and a medium large, something like that. This one has an adjustable strap in the back. Show me again.
Okay. Well, I need more t-shirts than hats. So
got it. What size?
Large, bordering on extra large.
Well, that might be hard to do. We could send you an extra large, you could shrink it.
Sometimes that happens, but I generally do wear large t-shirts.
Large, okay. All right. If you can just email me a shipping address, then we'll get that off to you.
Okay.
Okay.
Thank you very much. Appreciate it.
Thank you, Jeff.
I'll
Much
use another
appreciated.
t-shirt.
Yeah. How's the weather in Maine?
Oh, it's good. We're actually experiencing some spring. You know, it's colder here. I'm in northern Maine, right on the Canadian border. Okay,
Oh,
so
wow.
it's like the Upper Peninsula. And so, yeah, 47 degrees latitude. And yeah, so the snow is just melting off our yard. I mean, you know, snow pile. There's still plenty of snow on the ski hill. We have a little downhill ski area, but they closed it because the kids were bored. They were starting to ride their bikes on the sidewalks because the snow melted. But we have not seen 60 degrees yet. Between October and now, it doesn't get above 50.
Yeah, we've had some really warm days, but then the next day it might be cold again. So just like I was up in Traverse City in northern Michigan, Monday through Wednesday, and it was freezing cold out there. I went fishing out in some freezing rain, and wind and all kinds of nasty stuff. And yeah, the Saturday before that, I got sunburned fishing on the Detroit River. So go figure, huh? Anyway, thanks again. Appreciate it. Okay.
Thank you.
Thank you. Okay, business part of the meeting. I just got two things, and the first order of business is it's April, and that means it is officer election time. You notice I've sent out an email looking for nominations. The only thing I've got is that all of the current officers are willing to serve again for another year. They've all been nominated and seconded. However, one thing to note is that Brian Autumn has not been able to do much as vice president. He does do a lot of stuff regarding astronomy at the beach, though, so not like he's not a very active club participant. So, but he did realize that he wasn't really able to do much as vice president, and said that if somebody else would like to be vice president, he would have no problem stepping aside. So we're still open for nominations. Is anybody interested in being nominated for that, or any other position for that matter? And as usual, I hear silence. So, being that there are any, then we can, by show of hands, make a motion if somebody wants to adopt the slate as proposed. Does anybody know who the officers are?
Yeah, whatever. I make a motion.
What?
Make a motion to adopt, like.
Okay.
I'll make it. Ken, go next.
Okay. So one of you supported, one of you moved. So, okay, all in favor? Please say aye or show of hands. Is anybody opposed? Darn enough, I was going to get out. Thank you, Doug. Okay.
I voted both times.
That's true. Isn't that election? Yeah. Okay. Thank you very much. And just one other thing, just want to remind everybody that next month, just like, you know, we can't get here and settle down right away. We are actually going to be over at the U of M exhibit museum Planetary. And that's just for next month. And then in June, we'll be back here again. And then strangely in July, we're over at Eastern Michigan at Scherzer Observatory. And then finally, we settle back here for the foreseeable future, just so you know. That's all I had. So I will go to officer, starting with Jim.
We've had a couple of successful member nights, and hope to do that as much as we can on into the fall. The open house for tomorrow night is very definite, probably not, maybe. You know, there's going to be some clearing tomorrow night, but whether it happens in time for us to do anything for the public, that remains to be seen. The forecast is it could be raining at sunset. And if that's the case, then obviously we won't be going out. But I will send out an email by 4 o'clock or earlier tomorrow afternoon.
Yeah. Okay, we're just trying to figure out what.
One other thing I want to mention, because some of the emails I've seen of people have been a bit confused. The open houses are on the Saturday nights that bracket the new moon. Sometimes it doesn't work out exactly, so we'll be observing it first quarter, like that's what we'll be doing in June. The other thing is member nights are for members and their guests. So if there's somebody you know, a relative or a friend that has some interest in astronomy and might enjoy coming out to look through telescope on a Tuesday or Wednesday or whatever night, bring them along. They may end up being a lowbrow. And we'd certainly welcome their $35 anyway. But the the member nights are often the most interesting nights that we have out at Peach Mountain. So if you can manage basically a school night, come on out. It's a lot of fun. And that's it.
Thank you, Jim. And I'll move to Dave, and thank you for doing the minutes.
Yeah, so although there's I want to contradict it, the place that used to be called exists.
Oh, that's true. Thank you.
So it's the U of M Museum of Natural History. Probably your best bet if parking would be the Palmer lot. The dental school parking lot is out of the question, so the Palmer should be. So the second thing I want to bring up, we have been in communication with the Hands-On Museum, Leslie Science Center, Detroit Observatory, and the Museum of Natural History about the idea of having different kind of collaboration. Often it's going to be some event that would be during the daytime, weekend. So I think the first question I have is, we can establish if there are people that, well, we don't have any specific dates quite yet, but would people be willing to show up for some of these sorts of things? So we've done things like at the Hands-On Museum, Yasu brought a portable planetarium with the telescopes out. For the Hands-On Museum was like the Ann Street parking lot. So maybe the thing to do would be, I could send out an email and just, first of all, find out who's interested, and we might even have a separate email list just to figure out what dates we might want to do that.
And I think one thing that'll help as far as recruiting is knowing what kind of hour of the day these things are likely to happen.
Yeah.
If it's evening, then you've got a whole lot of people that are available, but if it's during the day, that's something people have to know before they decide.
Yeah. So, but we'll try to, gradually figure this out. So it's a little bit of a transition because we haven't done any of these things because of the pandemic.
Right.
So I think it'd be good to start up. That's something we can. Oh, and one thing I did forget here. If anybody's interested, I have 4 complimentary passes for the museum planetarium. So if anybody would like one or more of those. Okay, that's it.
Thank you, Dave. Our newsletter editor, Amy. Great job with the newsletter.
Nope, nothing. Just thank you for your submissions and please submit more.
Thank you very much. Jack.
Just quick update on the observatory. First, some of you know every year we do the Michigan Math and Science Group out at Peach Mountain. And that's run through Shannon Murphy does that through the outreach department there, Department of Astronomy. And there's going to be 2 sessions this year. And the date for the first session would be Monday, July 3rd, and the rain date is Thursday, July 6th. The second session would be Monday, July 31st, and the rain date is Wednesday, August 2nd. So those are the times we had worked out for Michigan Math and Science Group. The only other thing I have is some stuff that was bought for the observatory that we talked about. One, it's a group of things that were purchased. The moving blankets for the 17.5 inch, then we've got another blanket for the 24 inch. Over the years, 7 or 8 years, they've gotten all torn up, so those have been replaced. Then the standard battery pack for the Argo Navis and the Telrads, the other ones, because we got 3 or 4 scopes there with Telrads on them now. And then the old weather forecaster we had, I donated that years ago, but it died. It was not giving us correct information. So I picked up a new wireless weather forecaster. It also has temperature and humidity. So we're going to get the exact humidity on the hill. So instead of looking at your weather on your cell phone, trying to figure out what's going to be the humidity, you can look at the output and you can turn on your dew meter before it gets damp and dewy on your telescope. One of those things, we had to get a new surge protector for the surge protector that goes into the base of the fan. The other one, the lights went out of it and started flickering, and I thought, well, that's a bad sign. So we got a new one. It's an industrial grade cobalt. Now, for the total of batteries, surge protector, the blankets, cord for the wireless weather forecaster, it's not battery operated. Total for that came to, with taxes and everything, came to $123. And I just sent that all to Doug Scoble during the week. He ran it through, sent me everything back. And that's what the club will pay us $123 for all that stuff. Other than that, that's all I have to report on the observatory for right now.
Okay, thank you, Jack. Jeff.
Well, tonight was actually kind of different. We had, well, a peak of
25
in person and 18 Zoom, which interestingly is kind of a swap of our normal 70-30 Zoom versus in person. So, I don't know if it's the Detroit Observatory, better parking, better weather, who knows, but we did well. The other thing is the new website is coming along. There's more and more stuff I keep adding to it. The photos and all that will probably end up splitting out. I think we might be able to, if you wanted to see it, I can either show it on screen now or after the meeting and all that to go through it. But it's looking good. Starting to get a feel for where the categories are going to end up, and there may be some splits. Like right now, our member photos are just ballooning like crazy because you guys generate a lot of photos. I don't know if you know that, but if you start capturing them off the emails, all of a sudden they start adding up like crazy. Those will probably start separating into maybe like silver or planetary. So, other than that, nothing else really comes to mind. Other than that, we're kind of figuring out how all the AV gadgets work in this room.
So far, we'll get it down.
Yeah, another meeting or two, we'll get it down.
Yeah, exactly.
We'll forget everything by June. So.
That's true. We got a month to forget now. Thank you, Jeff. And I see in the Zoom audience, Brian.
Yes, thank you. Not much to report. Astronomy at the beach is proceeding, and we're looking at a potential keynote speaker of possibly Paul Gross, the weatherman from the TV that you might remember recently retired. He loves science, and so that is one possibility we're kind of excited about, but. Other than that, we're cruising along, planning the astronomy at the beach, which will be in the middle of September. I'll get you the exact dates.
22nd and 23rd.
22nd, 23rd. Thank you, Jeff. So.
How's the fundraising going?
Excuse me?
How's the fundraising going?
The fundraising is slow. We're kind of waiting for the IRS to come through with our 501c3. We have filed the paperwork successfully. We have a number. We are a 501c3, GLAC, right? It's wonderful. the last step is for us to appear on the official list of 501c3s that everybody goes out and looks for, and then nods their head and say, yep, they're deductible. And companies especially need to see that before they really kick in. So we're kind of waiting on that. But we have to thank John Wallbank for all of his tireless efforts dealing with the government bureaucracy.
Yes.
Mhm.
But I'll have more later as we get closer to September.
Okay, thank you, Brian. Nice to see you on the screen. And I do not see Doug, our treasurer, in the audience, which means he ran off with the money, no doubt. Actually, he might be on his way back up to Michigan right about now when I think about it. And I don't see Krishna. So, does anybody have anything else they need to bring up? No? Chad.
Quick one for Brian. Are you still doing your program on August 25th at AADL?
Yes.
Moon program?
Oh yeah, we're doing the big moon. Oh yeah, we should probably talk about that. Yeah, but Amy's there in the audience, isn't she?
Yeah.
Okay,
So
fine.
we're still planning to do it if the moon is, if it's clear,
Yeah.
Wednesday night. If it's not, it'll be Wednesday. If it's not on Wednesday, it'll be Thursday. And if it's not on Thursday, it'll be on Friday.
So the backup date
Tuesday, Wednesday, Thursday, or Friday. We sure hope it's Tuesday, but I guess we'll call it, what, maybe Sunday, Brian? Sunday or Monday, we're gonna wait.
Yes, we'll put the word out, but we did a successful test where we set up the telescope and the camera during the daytime on the sidewalk, which generated a whole lot of interest of passerby. Like, what's that? And we just showed a nearby building and then projected it up on their huge screen. So it looks great. And the moon's gonna look really cool.
I'll send an email. This is supposed to be Tuesday night.
April 25th.
From what do you say, 8:30 to 9:30.
This Tuesday.
This Tuesday.
That's good.
So yeah.
Ann Arbor District Library, sorry, I'm
Which
at the main downtown branch.
they've got a
So
bunch.
Brian will be out on the sidewalk and the screen is just in the front doors to the right.
is that the?
It's just for fun. It's just the moon and it's just because. No event particular, no celebration, something.
Kids can freak out.
Okay, anything else?
Just to announce that
I just joined, I think, yesterday. So I talked to Doug.
Welcome.
Thank you.
Thanks. And actually, if Doug was here to give us a count, you might be our 200th member.
Really?
I think you're 199 or 200. Yeah.
Actually, we counted up the folks that were whatever we passed it to. It's now 202.
Oh wow.
And I just out of curiosity, I sent some emails to the various GLAC members and the Kalamazoo group. And Kalamazoo, I think, tops it at 294 members. We are at 202. I think the Ford is around 150, something like that. And the Warren group was around 80, 90. And Oakland is around 70. But all of them across the board have all said that they've seen steady increases in membership over the last year since, kind of COVID eased up a little bit last summer. So that's encouraging news for all astronomy groups.
Yeah, so it's not just us growing. That's good.
Right, we're all on the rise, which is great.
Yeah.
Right.
I wonder if any of the other club members and the other ones will go into the transfer portal. Maybe we can pick them up and
That's John line coordinator.
Yeah. Anything else? Okay, before I entertain a motion to adjourn, just a reminder, at least for the people here, that it looks like they are doing tours of the observatory as we speak. So you just basically go out or turn a right, and there's an elevator and a staircase going up there if you want to check it out. So with that, I will entertain a motion to adjourn.
Let's go. Motion to adjourn.
Okay, support.
Let's go.
All in favor? Okay, thank you very much, everybody.